So Mark, when we first discovered -K technology, I mentioned earlier that I put it under my turntable, the original -K platform. And you gave a lot of advice to people around the world that would talk to you at shows, and you advised a lot of people to use it. A lot of people started putting them under their turntables. But then when we brought an original platform into our lab and we used some very sensitive testing equipment, we discovered that when you place a turntable on top of a -K, yes, you get a significant improvement in performance. But because the turntable has its own mass, it's its own entity, there is actually an energetic interaction between the platform and the turntable that's not ideal. It's better than not having a platform. But if you're striving for the ultimate level of resonance mitigation, we had to go beyond that.
So if we were to stack, the turntables can be really tall, big heavy platters.
Yeah.
And some platters are starting to get 300 millimeters in height. Some are 150 millimeters in height. Drums, and they've got a large mass. Now, the bearing point can either be high up inside that platter, or it can be down at the bottom with a long shaft.
Okay.
So sometimes you'll see the bearing shaft a good 150 millimeters in depth.
Okay.
And then you've got about 150 mil of platter. So imagine that's spinning, and it's doing this, what we call precession, the spinning top.
Well, that was so interesting when we discovered that with this equipment that we have, because with the naked eye, you can really look at it and you cannot see it. You cannot see it moving apart from its rotation.
Yeah.
But we found that once you put accelerometers on there and sense it, that there was actually a lot of wobbling going on.
Yeah, wobbling, and that energy, if we were to split the platter into four and nominate the quadrants, you will see, like a 1, 2, or 1, 0 mode, or going across this rotating mass that's processing, and it's pulling energy to the sides, front and back, and it's loading up what it's attached to, and then reflecting that energy back into the system.
Well, but tell me, why did you bring that topic up about having a lot of mass? Because
typically
sitting on top of the -K,
you want to add mass to your platter to get flywheel stability.
Absolutely.
And you assume that putting more mass is better. If I can do a 20 kilos, why don't I go to 40? If I go to 40, why don't I go to 80?
Yes.
Or why don't I go to 200?
Yes.
At some point, you think, well, then it's not going to be disturbed. But the very fact that it's spinning, it's then creating its own energy and its own vibration. And the point at what that levering point is above the deck creates more excursion into the base. So
I was just going to also say, Mark, that if you were to look at any material, whether it's metal or Corian stone, whatever you've got, the only way you can avoid some of these energies moving would be if there was perfect density consistency throughout the whole material. And even then you'd have forces because it's centrifugal forces.
Perfect machining.
But nothing in the world has perfect density, down to a sort of a molecular lattice level. It doesn't.
No.
There's little, if you look in a microscope enough, you can see there's little areas of high and low density in pretty much any material, unless it's been specifically made. So you're talking now about those energies, and I think you're also talking about the need to lower the center of mass.
All of a sudden looking at that toppling moment, the precessional moment, and lowering it as close as possible to the deck height, and then balancing that force with mass that is greater than the rotating mass.
Okay, so what do you mean by that?
So if we were to stack up the platter high and we put in more and more mass into the platter, then we've got more energy that's pushing and shunting around the base where you bolt your bearing to.
Right.
Now either the bearing goes through or the bearing goes upright, but you've still got that coupling. So that high mass spinning creates its own vibration.
Okay.
And when those energies on those quadrants gang together, you can get a vertical bounce occurring because of the Young's modulus in the material. And that can start to affect mid-bass from the measurements that we did. And to remove that signature, you have to lower your center of mass.
Okay, so we have a platform that is, as discussed earlier, the best that we have found, to the best of our knowledge, in mitigating up to 100 hertz.
Up to 100 hertz,
okay?
yeah.
And you're saying in order to avoid creating other vibrational issues, bring the center of mass as close as you can to the top of the minus K point.
Yeah.
And that's why the Dohmann turntables do not have a big drum style platter.
We looked at that because it's a classic way of addressing the problem. You go, I want more mass, and you start going higher, but it creates its own issues. And if you want to avoid those issues, then you've got to start bringing it down. So in this case, around this infrastructure here of the minus K, we've created mass distribution, and our platter mass is lower than the chassis mass.
And that's a big secret, or no longer a secret.
No,
if you understand physics, it's a
disclose
big,
the ratio of it.
Point.
But I mean, any engineer who looks at the helix can see that.
Yeah, can see the distribution of mass.
Can see what they. It's transparent. And in fact, we've got a window in front of the turntable which says,
have a look inside.
Come and have a look.
Well, so at the moment, what I'm leading to here is that first thing you did was you asked minus K to modify the design.
Yeah.
For Dohmann, for your design.
So they make a number of units, as you know,
and
some are very big and now very slimline units. But to fit the infrastructure in of a turntable, we worked with minus K, and they were fantastic to work with, where they modified the design without affecting the performance to allow us to fit in our ancillaries like our motors, our arm boards, and other control electronics, etc., right closely packed around the core, the central core, which I mean I can go in and describe.
We'll talk about that in a moment.
How that works. So this is a custom build.
Absolutely. So the first thing you did was you had the design modified. The second thing you did was you integrated the design, the minus K, into the chassis at critical points within the turntable. And that brought them together as one.
So we've got this working up to 100 hertz. Then, knowing our processional mass causes vibration issues above 100 hertz, how do we address that through the chassis? So there's a balancing of the forces, and then there's a way of absorbing the noise. From the critical subsystems.
Well, before we go there, maybe just explain how the minus K works.
It's completely passive. What we mean by that is that there's no electronics trying to sense or move something in an opposite direction.
Nor is there any electrical fields that you've created or anything you need to filter.
Dead quiet. It's also what we call zero outgassing, so you can put it into a clean room, making chips, for instance.
Okay.
That's not potato chips; that's computer chips.
You can operate in hazardous environments.
Yeah, I don't think
not that you'd be playing turntables in a mining site. But.
Around its centre core is a coil spring. Is a classic round coil spring.
I can just show it to the camera.
People can see in there.
Absolutely.
Now, if you were to use that coil spring, and say we placed a ruler on here and we push down on this side, or we push down on the opposite side, it's like the playground, the teeter-totter in the playground where seesaw.
Seesaw.
Now, the problem with that is...
the visual of you on a seesaw in a playground has just disturbed me.
Those days are over, George.
Just continue.
I'd need to be balanced from the other side. So you get that motion, but you also get a lack of control in forward and aft and the diagonal motions around that central hinge point.
Yes.
So in order to overcome that natural desire of this thing to topple, they use these flat, what we call blades, and they constrain the mechanism to work only in the vertical plane.
Only in that plane, yeah.
And the mechanism, at the fundamental core of it, is an overloaded spring.
Okay.
Because just before the spring collapses and stops working...
It's literally like loading up a car or a trailer to the point where it just gives.
Sags, yeah. Just above that point is its lowest natural frequency. That's how they achieve this. Now, they can adjust by means of tension on the side the resonant frequency by putting a bit of pressure on these plates here to create a slight upward force. So you've got effectively a bending plate here, and before it snaps straight, that's then stiff. Just at that point, just before she snaps straight, is its lowest, softest, most compliant mode. So we've got that handling the vertical component, and the innovation then is using these columns that are located on the outside corners, and that creates a horizontal and torsional mode. Yeah. Again, with enough weight compressing on it, these get close to what we call the buckling point. And the buckling point is the point they call it negative stiffness. Yeah. A Euler spring, or minus K is the actual symbol for it. Yeah. That's why the company's called minus K. Okay. It's that hovering above the collapse point that it does. And David Platis, the original inventor of this, the idea came to him whilst he was walking down Huntington Pier in Los Angeles there with his wife, and he somehow had what happens if there was a earthquake? Right. What would happen to the pier? The pier, would sway, and then in his mind, that's exactly what I want to happen. The pier platform would stay stable, but the platform could move in every plane. So that then led him to separate the two modes.
It's ingenious, actually.
It's absolutely ingenious. And his legacy is continuing with the engineers that now work there, Eric Runge and Steve and the team. They're able to continue this innovation, get them platforms into thinner heights and so on. They can build these up to several tons of load capacity. So it's not limited. It's built for the range of payload. So in this case, Minus K built this unit specifically for our chassis payload.
Yes.
So there's
it's been
very closely
tuned to that
matched interface between the two systems. So this beautifully transitions up to 100 cycles, 100 hertz. Then we handle the vibrations higher order from that using other techniques. But the downward forces and the precessional forces with the load balancing
with
and
the mass being below, the center of mass being lower,
means that we create a stable platform for it, and that's really the art, and it led to the shape of the turntable as you see it. Yeah. In the Helix 2, it's all hidden in behind the cover, but it's the same system. Internally in there. So
no, I think that's very well explained, Mark. I'm in awe of when people like David Platis have that moment. Just like
Sweet
I'm in
idea.
awe when you and I are having a burger somewhere and you get that look on your face like, I've just thought of something.
Just thought of something.
Anyway, that's great. Well done.
Yeah, you
well,
don't know where
well
you are when
explained.
the thought comes through. So,
Well done.
but yeah, I'm absolutely enamoured with this system, both from a technical perspective, as any engineer would look at something,
Absolutely.
but from a musical perspective, and I can't live without it.
Yeah.
For what we do. Yeah.
Absolutely. Well done.